Hello and welcome to the KIM Resurrection series, part 10. In this episode, we'll be continuing the repair of the keyboard. Now, you might recall at the end of the last episode, we had data coming out of the keyboard, but the processor didn't seem to be seeing it at all. I've managed to find out what's wrong. On the top left here, you can see the oscilloscope reading, let's make it a bit bigger, of the phase 2 clock. And you see it jumping backwards and forwards. I've mentioned this in previous videos, the way it jitters around a bit. It's causing a few issues, I believe. Well, we have some very close timings on the 6502, and if we go to the actual book where it shows them, let's move this out of the way, we've got this table here, which is all to do with the timings of the read. You've got the right one up here and the read. I think I've been here before. So the CPU will put its address out here where it wants, and then you decode that, and that tells you what chip select to have, etc. And then you get the data and you put it on the data bus, ready for it to be read in supposedly on this falling edge of the phase 2 clock. There's a few caveats here. At the beginning here, it says you cannot guarantee the address until 350 nanoseconds after the rise of phase 1 pulse, which should be slightly after the fall of the phase 2. Also, on my board, there's a 50 nanosecond propagation delay here from when the address is true to when the K7 and K5 chip selects are valid, and that's just a delay through the gates. So up to, I cannot guarantee anything until 400 nanoseconds after the rise of the phase 1. Well, I don't actually monitor the rise of the phase 1 in my chip. I monitor the falling of the phase 2 and assume that's phase 1. And they may well be very close together. Anyhow, you've got 400 nanoseconds, so I'll read everything there and see what's needed. If K5 and K7 are not selected, then it just loops back round again and looks for the next phase. If they are selected, then I've got to read the data from either the ROM or the IO or where RAM, whichever, and put it onto the data bus. But this isn't quite to scale. This 400 nanoseconds is nearer here. And so I've got this period here in which to put the data out. Now it says here I've got 100 nanoseconds minimum from the phase 2 clock falling to 2 volts, and when the data's got to be valid. So I've got until 900 nanoseconds to get my data out. So between 400 and 900, so that gives me 500 nanoseconds to find out what data it needs, find the data and put it on the bus. Well, you may recall I mentioned in some earlier episodes that I was a bit worried about the timing of the RAM and the IO ports on the cloned Riot chip. Well, I went back to this software and I rewrote some of it and put bits in some different orders, etc. And I made sure everything fitted to this timing and the right timing up here. Everything was there, everything was in the correct windows. Well, the ROM reading, normally the ROM comes out about here, the data from the ROM, it's fine, and the RAM about here. The IO is a bit closer to the edge, but it was well within spec. It was less than 800 nanoseconds before that had come up. It was on the bus within 800 nanoseconds, so it should be well within settling time and reading. There's also another delay, is the Riot chip puts data out. It has to go through a buffer chip, which I worked out as about 8 nanoseconds. Actually measured it, about 8 nanoseconds delay. And actually get them to the data bus. But there's also the rise time of the data bus, which depending on what voltages you're reading it, could be anything up to 45 nanoseconds. So again, that's pushing this line here further in that direction. So I've got to get the data there even sooner. Well, I managed to get everything within the specifications written here. But as you can see, the phase 2 clock has got a lovely jitter on it. It's moving around. And this is the phase 2 clock going out to the Riot chip. The one that's actually used on the CPU has got slightly different timings because this signal is from the inverter chips. So let's see if we can get the phase 2 from the actual CPU up. And as you can see, it doesn't quite line up. So the phase 2 on the IC, on the 6502, will actually be trying to do its sampling here and not there. So that's another difference in the signals that could cause issues. Though all these bits added up seem to be giving me problems with reading the I/O ports. So I revisited the software and I chopped and changed a few bits around. One of the things I did was, here with this delay here, is instead of reading the address after I'd got the K5 or K7 signal, I read it before, because I could read it 50 nanoseconds earlier. So I was reading it at this point here, and then checking for the K5 or K7 signals. Thus that gave me 50 nanoseconds there. There's a few other little bits and pieces in the code I was able to jump around. The actual data bus comes out of port A, which unfortunately on this particular microcontroller has got the bits all split up, so I have to do a bit of shuffling of the bits before I can put the data out. And I was tidying the data up before I was putting it out. Then I realised the pins that would have the noisy data on weren't actually connected to anything, so they didn't matter. So I was able to save a few cycles there, and all in all I saved about another 80 to 90 nanoseconds off the time to get the data there a bit sooner. And that was what was causing the issue. We look at some of the timings on the sheet we got here. We turn this one off and go back to this one. And if we turn off the oscilloscope. So here's the logic analyzer sample. Now this is with the newer software in, so this should work a bit better. But we had, when it's cycling round, actually look at some of the software. I'll show you the code, what it was doing. I'll actually bring that over here. And I'll grab the other one to make life a bit easier, because there's two sequences. So the first thing we do is it does the initialization of the ports and reads whether there's a keyboard plugged in. If not, it branches down to this routine here. And the first thing it does is do a scan. So it comes down here, then it scans the keyboard, etc., the screens, the LEDs, whatever, puts them up. And then at the end, it jumps to this AK routine, which is sitting here. So what it does, it puts a 3 into the Y register, a 1 into the X register. And then here, it puts FF into the A register. Then it writes out the X register to 1742, which is port B. So he puts that out to port B, which selects row 0. I know it's got a 1 in there. Oops, sorry. Well, we're putting X out, we've got a 1 in there. But remember that it was 1, 2, 3 and 4, not 0, 1, 2 and 3. So it puts a 1 out there. Then he increments it. And then it ends, it reads it back in, port A, reads port A in, and ends it with what's in the A register. Now we know we're only using the bottom 7 bits, so instead of having FF in there, if there's no key pressed, we'll end up with 7F in there. It's okay. Then decrements Y and branch is not equal to go around again. It just loops around again, and this time, because it has incremented the X register by 2, instead of putting a 1 out, now it puts a 3 out, which is row 1. So it then increments it again, reads it in again, and it reads row 1. And it does that 3 times, reading row 0, row 1, and row 2. If none of the keys are pressed, you'll get 7F sitting in the A register. If a key is pressed, it won't be that. It will be a value less than that, because you lose the top bit, because of the top bit is never on anyhow. So then it comes through here. It loads a 7 into Y and puts that out onto port B. So port B is now looking at row 3. That row 3 that it didn't seem to do anything. Well, it doesn't seem to do anything here either. And then you OR 80 with the A register. That is turning that top bit back on. So originally you had 7F sitting in the A register if no keys were pressed. You now got the top bit on, which there should be FF for it sitting in there. Then does an XOR with the A register with FF, and that it basically inverts all the bits. So So at this point here, if no keys were pressed, A should have a 0 in it. And then you return from that subroutine, which comes back in over here on this side. And then it says branch if not equal. So if there's not a 0 in there, as in a key has been pressed, it will branch back up the start and it will just do the whole sequence again and again. And that's exactly what it was doing. All the time it was saying there's not a 0 in A, saying there's a key was being pressed. Well, if I press the key as well, it still looped around there. At one point I was wondering whether this a branch if not equal wasn't working, but it must have been because it was working up here. So I discounted that. But I was puzzled greatly and I thought, well, I'll tell you what, how about I modify the software slightly so that instead of doing this OR A with 80, I'll just make that move the A register into a memory location somewhere, just so it came out on the data bus so I could see what the data bus was doing. If we look back in the actual code, remember that big bit at the top where I had all the ROM, etc.? I modified one bit. I found that piece in the code. That's the actual part there where it's testing it. And I put this line in instead. It's commented out at the moment. And here, basically, it's moved the value in the A register into this memory location. And then all I had to do was monitor the data bus, the actual data bus on the 6502, to see what value we was getting there. We now look at the trace from the logic analyzer. Remember, similar one to this before, with here's scanning out the display, and here's the region of the keyboard. This is slightly different because this is the fixed version, not the broken version. And if we're looking closely, so this is row 0 we're looking at here. If we look along the code, we can find, there we go, address 1740. That's the port A register, reading in port A. When it was being read in, this one here, I've put channel 31 onto the phase 2 clock. What was happening is when this phase 2 clock came down here, this value here was sitting at that point. Right, so you see this 17 was sitting here. When it done a read on that address, this 17 was still on the bus at about this point here when the phase 2 clock came down and read it. And it put that 17 into the A register because the instructions further along here moved the A register and it had a 17 in it. So I thought, where's the 17 come from? And that's the only place it could have come from. And then when I looked at the phase 2 clock, I could see it was clocking in. So back to the software in the cloned riot chip and squeezing as many cycles out as I possibly can, I managed to get it so that, here we go, this is where I clear the register. So you can see there's a 0 there. Don't always need that. But now the data comes in at this point here, and this is the clock where it's clocking in. Because some of the times with problems we had was this phase 2 clock jitters around. So I was putting the data out within specified times, but the phase 2 clock falling edge was moving. And sometimes it didn't read it, sometimes it did. So I've had to tighten up the timing on my clone to fit this phase 2 clock that's moving around a bit. You know, I was touching the board and making the computer crash. Let's see if I can show you something else. Yes, here we go. We just swap back to the other display. I'll just drag it over to this one on top. It's easier. Now you watch the phase 2 clock. What I'm going to do is I'm just going to press on the edge of the circuit board so the board lifts up, and press on the bottom edge so the top edge lifts up a bit, and watch the phase 2 clock. So I'm wondering whether the jittering of the clock is all to do with just capacitance between the board and what it's laying on at the moment. Maybe I should put it on some feet, because that is a massive difference. I'm pressing that and the top of the board is lifting about an inch off the surface it's on. So I think that might be what's causing the jitter on the clock. And that is causing time issues. You know, when I've been pressing a board and it crashes? Well, it's reading the wrong data in. So it's all to do with the mounting. So here we have the KIM-1 running. Oh, and it's crashing. Reset it. And now I'll press the keys. it reads something. Let's put all to 1, shall we? You may notice I've got a few segments missing. This bottom segment here is gone, and over here there's a couple there as well. Let's put the 8s back in and you'll see. Where's the 8 gone? Oh, there's one segment there that keeps coming and going. That top one there. These two. Let's get me pointy stick. I found my pointy stick. So this segment here is definitely dead. These two down here don't work, and this one up here, sometimes it comes on, sometimes it doesn't. But so I've got to try and source these. The only ones I've found have been like £30 each, which is a rip-off. What I might do is, if I can get ones with the same pin out, is replace the whole lot with the same type, so it all looks neat and tidy. Shame they don't work, but there you go. I've actually measured the voltages across them, and the LEDs are going short circuit. Oh, there we go, that just failed. Saw that one up there. That one there fell. Different numbers across. Ah, it's going. And oh, I crashed it again. Reset. And with this switch switched over, it actually does stuff as well, which it wasn't before. So seem to have made a bit of progress with this. Alright, now on to the second issue, is why has it crashed? It's crashed again. But if you actually do a data analysis on that, so if we run up the data logger, okay, we've just fallen over, so let's do a sample now. Because it sort of stops updating the display, but it hasn't actually crashed. So let's see what we got. We've got some funnies going on. There we go. We're still running. This is code. It's running around in a loop. And that is trying to decode the keyboard into a hex and display it, but it isn't actually displaying anything. I don't know how it got to this point. And every so often we get this, it does some loopy stuff here. Okay, let's see if we've got a full crasher on this one. And yes, right, this is when it's completely crashed. Again, we've got the phase 2 running along there, and zoom in, we've got some code running, and then here it's reading the interrupt vector, and then going to that interrupt vector, which it reads from here, which unfortunately has got a 0 in it. So it goes to that memory location, which happens to be the last one, and then starts executing from there, and that memory location has got a 0 in it. And it keeps trying to run things, but every so often it tries to run a 0. Let's see if we can find one. There we go. And this one here, it reads that in, it's a 0, and tries to run that as an instruction. Well, 0 as an instruction is the break command, and the break command uses the same vector as the interrupt. So it saves the address on the stack, and it then gets the interrupt vector, runs that, and does the same thing again, and goes through these lower memory locations until it reads a 0 again and tries to execute it, and therefore it does another break and goes round and round and round. I thought it was getting an interrupt first of all, and I tried measuring the interrupt line, and there was nothing on there at all. I put the logic analyzer on there, monitoring the interrupt line and the non-maskable interrupt line, and there was nothing on there at all. So I started investigating whether you could have a software interrupt. And yes, there's the break command, which uses exactly that vector. So for some reason, it's reading a 0. And I'm wondering if this phase 2 moving around, of the clock, or the clock pulse moving around, is at some point reading a 0 Now remember when I put out instructions onto the data bus? I'll put a 0, I'll clear all the bus first, and then I'll put the value out that I want on the data bus and so forth when I'm reading from the ROM. I'm wondering if it's reading this signal here before here. So you've got a phase 2 clock coming down there on the 17. Well, that's fine. But maybe sometimes it reads it back here when it's a 0. And then it goes, oh, I've got a 0 instruction, and does a break, and then gets caught in this loop. And that's what the crash is. Well, certainly that part of the crash. So I'm wondering whether the my emulated ROM is working well enough. So I'm going to modify this board, which has got the ROM on it already programmed up. This is a previous one I'm going to hack about. It's got the RAM. So I'm going to have this RAM as emulating the bottom 1K of memory that's on the motherboard, which I haven't replaced yet. I want to do that last. And then this will be the ROM that's in the write chip, but it'll be reading this one. I'm not going to have the write chip turned on when reading this. So this 74138 will do the instruction decoding. When we get a K0 come out of it, it will enable the RAM, as we're doing on the board that's plugged in at the moment. When we get a K7 come on, it will enable this ROM. So that will actually be running the code. We don't need the K6 signal because that is for the other write chip, which isn't actually doing anything at the moment because we're not using the tape connection or anything, so we should be okay without that. And then the K5 signal, which is for the I/O on the write chip, I shall feed that from here straight out to this pin here, which is connected to that AK signal, which enables the onboard address decoding. So when it's asking for the I/O or the riot RAM, this signal will go low and enable the onboard decoder, which will enable the write chip on the motherboard. And when it's asking for the ROM, instead of that signal going to the write chip, that will be disabled because this will go high. K5 will go high and disable this, and K7 will come on and enable this one onto the bus. So all I need to do is I'll remove that link, and we only need to use the one. This was set up to simulate the whole lot on the write chip, but we're not doing it that way anymore. So this is another little hack. So make another board. I'll just reroute the appropriate signals from here out, well, from that one actually, from there out to the appropriate pins. This one I think is already wired up. This one is going to be a wire link, and the one down to here will be a wire link as well. I might have to cut a couple of tracks as well. That should enable us to use this ROM, and which will be a lot faster than the cloned write chip. And then we'll see whether the timing's the issue. So I think I'll do that in the next episode, in episode 11. So don't forget to like and subscribe, and put lots of comments below, and hopefully I'll see you in the next episode.